Good morning. So, myself, Dr. Paula Shapui, Associate Professor, Department of Chemistry, SIM Institute of Science and Technology, Chennai. So, today we'll be discussing about macromolecular chemistry or polymer chemistry, which is very much important for BTech first year. That why polymer is very much important. So, according to Greek words, poly means many, and maros means mar or maros. It's called parts. So basically, polymer it's a long chain compound where a units will be repeated, same units will be repeated by covalent bonds. For example, ethylene to polyethylene. So basically, this ethylene part it is from the single bond and connected to each other. So how you can prepare ethylene if you use the peroxide as a initiator, then you can prepare that polyethylene. Both side it will be OH group will be there. Now, in 1920 or before that, polymer was considered as a aggregates. But in 1920 onwards, Staudinger said that polymers are composed of very it's a long sequence of similar molecules by covalent bonds. Basically, it is the modern definition. So, what is monomer? Which are the repeating unit in a polymer or macromolecules? I'll come to the point. What is the basic difference between polymer and macromolecules? And what is polymerization? The process by which monomers are connected to each other by sigma bonds. That's called the polymerization. It can be double bonds also, means triple bond to double bond or double bond to single bond. And the N means the number of repeating units called the degree of polymerization. Okay. And the basic requirement for polymerization is the monomer should have either double bond or it should have the functional groups both sides so that they will be connected with each other. So Staudinger first introduced the term macromolecules to describe the polymers, and he got the Nobel Prize in 1953. So this is the one molecule called lignin. It's a macromolecules, and you can see that how they are connected to each other. Of course, there is a difference is there. This molecule is not repeated, right? So macromolecule is basically large size, high molecular weight. But polymers also large size, high molecular, but it will be repeating unit. So macromolecules does not necessarily that they will be connected with each other. Same repeating unit will be connected with each other. So that's the basic difference. Polymers will be repeating unit will be there connected with each other. So all polymers are macromolecules, but macromolecules need not to be polymer. So how this functionality will be matter, because see in this case ethylene molecules, this double bond will be used as a connecting ligand, right? So ethylene to polyethylene. So if monomer have functionality more than two, then this can be lead to different branches will be there, or it can be network polymer. For example, if there are double bond or functional group in both sides, then it will be forming the chain. Even it is a possibility of that branched also along with that main chain. Even there is lots of branches also possibility there, because most of the polymerization are can happen in different branches also. And so it's a difunctional molecule, it is trifunctional molecule if it is tetrafunctional means with more and more functional groups, that polymer structures will be more and more complicated. So polymer nomenclature, you can see that isopentene, it will be connected that CH2 to all one CH, and this propyl group will be part of that. What is that called? That chain, or yes, so that can be called polypentene. Isoprene, which is the common unit of natural rubber. You can have that cis isoprene, which is natural rubber, and trans isoprene, which is not natural. Synthetic rubber you can consider. Nylons is the good example of the synthetic polymer where adipic acid and hexamethylene diamine, they will be connected with each other via condensation polymerization, and you can get that amide both sides. See, CO, CH2, CO. This is the adipic acid part and this is the amine part. So acid and amine, they will be forming that amide. Then we have the cross-linked polymer, which is the bakelite, discovered by the Bakelite in 1909. You can see it's a highly cross-linked. So it is formed by the formaldehyde with the phenol compounds. That condensation, another condensation reaction. So classification of polymers can be based on the origin or source, skeleton structures, molecular forces. So for example, natural polymers. So your proteins, or you can say DNA, RNA, they are natural. Starch, cellulose, they are natural because they found in nature, plants or animals. What is semi-synthetic? Little bit derivative will be there of the natural compound. For example, cellulose acetate. You can make it in nitrocellulose. That can be used as a polymer membrane. And synthetic polymer, it's a completely different. Means it has no connection with the nature. People will be synthesized in the laboratory, completely different, and they use either in their daily lives. So based on the structures also we can differentiate. Linear structure means there is no branch in ethylene to polyethylene. If it is branched, for example, polyethylene diamonds, as I told that there are more than when you have trifunctional groups, there is a possibility of branch structure. Cyclic structures, it's a kind of cyclodextrin is the one example, and network is your basically it's a highly cross-linked polymer, and that's called bakelite. So based on the molecular forces, we can have different types. For example, thermoplastics, elastomers, thermosets. What are thermoplastics? They can be molded. They will have certain melting point. They can be molded into different shape. So they may have melting temperature. They may have glass transition temperature. So for example, polyethylene, polypropylene, nylon, polystyrene, they are thermoplastic. Means you can make it in any shape, whereas elastomers basically cross-linked rubbery polymers. So they can be stressed just like that rubber, right? In any extension. So basically, cross-link density is less, and it does not have any kind of melting, but it will have thermal decomposition. So, for example, polyisobutylene or silicon rubber or polyurethane. And another one is thermosets. Thermosets are basically cross-linked polymers. Highly cross-linked will be there because lots of functional group will be there, and they will degrade before melting. So basically, bakelite, epoxy resin, and they will be highly insoluble compounds. And thermoplastics, mostly we are more interested because they can be easily molded. They can be crystalline and amorphous. What is crystalline? Crystalline basically molecule, same molecules, same unit cells. It will be repeated throughout the crystal lattice, just like bricks in a building. And amorphous is basically there is a short range order of periodicity. Okay, so suppose in a when a college is when that classes are over and students are allowed to come out, so that's kind of random element will be there. That's called the amorphous range. Now, uh, stereochemistry also it will be applicable to polymerization because based on the position of chain molecule chain functional group in a three-dimensional projection. So we can have different spatial arrangement of the repeating units. So that's called the tacticity. Tacticity basically arrangement of that groups, pendant group, basically that attached groups in space. So that can be different type isotactic, syntactic, or atactic. You can have very easy example. Suppose isotactic. So all these repeating units are in same side. For example, x is down, y is above the plane. This is y is above the plane, y is above the plane. So basically, in a chain of or in a polymer structures, when the same functional groups are above the plane, then it is called isotactic polymer. Isotactic polymer is very much important because they will have high crystallinity, high tensile strength, high molecular weight, and highly crystalline. Whereas syntactic, it will be alternate. You see in this case where y is above the plane, next case y is below the plane, then y is above the plane, then next case y is below the plane. It's a alternate element of the same functional group either above or below the plane. And that last one is the attractive polymer. Attractive polymer is a random element of that same functional group. It can be a, B, 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 A, B, A, B, like this. Alternate arrangement, not alternate, it's a random arrangement. That's called attractive polymer. Why this staticity is important? Because I told you that attractive means it is having the least crystalline materials, and it is a low density materials. Always it will have melting point, will be very low. So there are another way to represent the polymers. Polymers, for example, homopolymer. Basically, one polymer unit, monomer unit will be there. They will be connected with each other. That's called polyethylene, polyacetylene, polystyrene, all this. But when two monomers unit connected with each other and form the polymer, that's called copolymers. For example, adipic acid and hexane and diamine forming that nylon 6,6. So molar mass or degree of polymerization. So when you have polymers, a very long chain, you can have lots of fragmentations will be there. Means that a chain will be there in the main chain. So it is very difficult to find out what is the actual weight of the polymer. So we can get some kind of range of polymers because of the complexity of the chain structures. Okay, so we need to find out the degree of polymerization, means how many number of repeating units are there in the structure. So for example, if molar mass of homopolymer is a capital M, that we need to determine, and degree of polymerization is X, and M0 is the molecular weight of the starting monomer, then we can easily define it, right? So for example, there is method is called number average molar mass, where is the sum of the product of the molar mass of each fraction. So you need to fragment each polymers in small fragments, for which you can have the fraction value as well as the what is that molecular of that fraction value. Okay, and this fraction, it can be calculated by the ratio of in I by the total number of molecules. So Mn average, so basically number average molecular weight, that is summation of ni, means how many number of fragments are there, molecular weight divided by total number of ni. Another option is the weight average molecular weight, that is your Wi, that is Ni Mi divided by sum of Ni Mi. So these are the means kind of, I can tell, different method we can determine the molecular weight. Basically Wi, it is basically Ni by Mi, right? So it will be sorry, Wi equal to Ni by Mi, or Ni M square. Okay, so these are the different methods are there, but generally in laboratory we wish to get that molecular weight using viscosity, but that Poisson method, we wish to get that viscosity is directly proportional to time, and with respect to the time, how that time will be dependent with respect to different concentration, and from there we can get the what is the average viscosity, and we can get that eta I equal to k m to the power alpha, the Stroinic equation, something like that. And for every polymers there will be k and alpha, which are constant value. It is available, and we can determine what is the possible molecular weight range. Okay, so as I told that molecular weight of a polymer, exactly it is difficult because of the lots of branches will be there. So getting that exact repeating number, it is difficult, but we can get approximate, suppose 30,000 to 40,000 or 50,000 to 60,000, that molecular range we can calculate it. Okay. So this ratio, weight wise molecular by number of molecular, that is called your polydisperse index or dispersity index. Okay, and that value, you can see if you just plot the molecular weight divided by mi by ni, and you can get number average molecular is always higher value compared to weight average molecular is higher compared to number average molecular. But number average molecular, you can see that more number of molecules will be involved. So that's the kind of information. So what are the different types of polymerizations? So already we talked that addition polymerization means that polymers, they will be connected with each other, repeating units, and another condensation basically that water molecule will be lost, right? So adipic acid and hexamethylene diamine. Then this also that how it is synthesized based on the synthetic methods. We can means divide into two parts. One is called step growth polymerization, that is mostly in condensation polymerization. So basically polymers change their growth by stepwise reactions between the two molecular species. And chain growth polymerization, basically polymer chain grow only by reaction of monomer. So it's a addition reactions. Okay. So chain growth polymerization, you can see that two molecules will be connected with each other, two chains will be connected with each other, right? And step polymerization, so basically that 2 plus 1 3 3 plus 1 4, like this it will be going on. So what is the basic difference? Addition polymerization, basically monomers will be single monomer. Condensation polymers, two monomers. It will be in addition polymerization, no additional products will be formed. For example, water, ammonia, HCl, acetic, ethanol, methanol. But in condensation polymers, these additional products will be formed. So in addition polymerizations, it is basically same monomers, but here minimum two monomers with functional group should be there. So addition polymerization is described by chain growth polymerization, and constant polymerization is the step growth polymerization. Okay. And addition polymerization example polyethylene from ethylene, whereas conventional polymerization, it's called nylons is the good example, hexamethylene diamine and adipic acid. So let's understand the what is the mechanism of addition reaction. So basically, we need a radical initiator. How? Using free radical. There are free radical polymerizations where we need radical. So radical from where we can get the peroxy compound or hydrogen peroxide. So this ester group, not ester, I can tell peroxy, butyl peroxide or benzoyl peroxide group, under heating condition it will give the radical, and that radical will be bind with the alkene or yeah, basically monomer, and it will form the radical will be initiated, and then radicals will be connected with the another alkenes, and this radical will be continued. And when these radicals, two radicals will be combined together, and you can get that full chain monomer units. So you can see this is that one radical, this is another radical, they will be combined it. So this is the but problem is free radical polymerization means that you cannot control the molecular weight. So it can have any positions. It can grow it. Okay, highly branched structure it is possible, and in fact in this process, atactic polymer or low density polymer is also possible. Whereas in ionic polymerization, basically cationic and anionic. So cationic, basically you need the Lewis acid, for example, hydrochloric acid, boron trifluoride, arsenic pentafluoride, or aluminum fluoride, or sulfuric acid. So what is happening is, in presence of acid, this alkene moieties, it will be forming the cations, and then alkene will be attack on the cations, and in that way, these cations will be grows. Okay, and then in case you want to stop, so basically you have introduction of initiator, then chain propagation, and then termination. When you feel that okay, polymer is formation is over, then you can add that on base, suppose hydroxide ion, sodium hydroxide, so it will be stopped. Similarly, in anionic polymerization, you can use that butyl lithium organolithium compounds or hydride or mostly butyl lithium compounds or any kind of base you can use it. So it will be forming that anions, okay, and it will be continued because that anions you can attack on that another alkene moieties and you will be getting these anions and it will be continued. And in termination you can use that proton. So basically it's a cationic and anionic polymerization. Basically they are complementary to each other or reverse to each other and you can get that polymers. So when you want to stop it, that time you can use that acid. But again, ionic polymerization also another case that where attractive polymer or chain polymerization is more possibilities there. So if you want to control this polymerization or if, specifically you want to prepare syntactic polymerization, then you have to use, sorry, isotactic polymerization, you have to use this Ziegler-Natta catalyst. So Ziegler-Natta, they have used the catalyst which is called TiCl4 zinc bromide or aluminum chloride, where Ziegler-Natta it is used as a, this is the mechanism, basically a little bit complicated mechanism. So basically that alkene moiety they will be combined together and form on the monomer on the titanium side, okay, and there is no other side is there, so only this that chain will be grown. So this method is highly useful. Specifically, it will form highly stereospecific structures with high mechanical strength, high melting point, highly crystalline polymer. Even you can get high density polymer here. Condensation polymerization, it is comparatively easy. So here you need a functional groups from both sides and they will be interacting with each other, and in a typical condensation reaction either water or ammonia it will be coming out, and you can see hexamethyl diamine, it will react with adipic acid, it will form that condensation polymerization. So basically one water lost will be there. Similarly, what is copolymerization? Copolymerization basically the two monomer units they can be connected with each other, and for example butadiene and styrene. So you can get that butadiene styrene copolymer. So basically two monomer units they will be connected with each other. Okay, so that's called the copolymerization. So here we will be discussing a few cases where polymers, how it is synthesized, what is the uses that will be discussed. So for example, polypropylene. So for polypropylene, you can use Ziegler-Natta catalyst to get that isotactic polypropylene. So basically here, you have to take that propylene and you have to use the Ziegler-Natta catalyst and you can get that polypropylene. So what are the properties and uses? You can just check in, especially uses. Their fibers were very strong and fibers are used for making road, carpets, blankets, all these things. Next one is the polyvinyl chloride. So polyvinyl chloride you can easily prepare from acetylene and hydrochloric acid into mercury chloride, and this polyvinyl chloride, once you get the polymerization, you will get PVC. PVC is highly useful as a that polyvinyl chloride plastic PVC pipe. It is highly useful. It's high rigidity and chemical resistance, and it's of course it's a brittle in nature. Then we can talk about styrene to polystyrene using this peroxide linkage initiator. We can get the polystyrene. Uh, Polystyrene does not have any issue with the. It has problem with this biodegradability. Okay, in fact, highly used in food services. So medically, it uses sterile test tubes, diagnostic components, and thermal insulations in refrigerator freezers. We can use it. And then Teflon is basically polytetrafluoroethylene. It is formed by under pressure and it will be formed from benzoyl peroxide. You can get tetrafluoroethylene. What are the uses? Basically, this is highly insulating agent and insulating motor. It is transformer. You can use it. Cables, wire. We can use non-stick coating, cookware coating. Also, it is used as a Teflon. And then nylon, what is the difference between nylon 6, nylon 6 and nylon 16? So nylon 6 basically adipic acid and hexandiamine, it will be forming amide basically. But nylon 16, so with 16 basically you can have hexendiamine with the uh, sivacokyl chloride. So one molecule, for example, halide is your carbonyl halide is your 10 carbon, whereas amine is your 6 carbon. So you can prepare nylon 16. Highly useful in jeep fasteners, electrical insulator, all this. And nylon 66 you can prepare from caprolactam. So basically you can do the hydrolysis and followed by polymerization. So you can get the nylon 6. So it's a monomer unit. Pteryline is your para-hydroxy or carboxylic acid with the ester group, right? So basically carboxylic acid and this ester group. So that's called that polyethylene terephthalate. Polyethylene terephthalate can be combined together. So basically it is low permeability to oxygen, carbon dioxide, water, and it maintains that good shelf life. And recyclability also quite good. It can be saved into different steps. So polyethylene terephthalate, it is first of all resistance against chemicals such as acid, base, or heat for manufacturing of shopping box, bags, water bottles, containers, microwave containers. All these are used. And the last, not the least, polyurethane. Polyurethane basically you need that aniline and you need that uh, oxyl chloride. So you'll be getting a COCl2, right? CO Cl. And finally, on water loss, you can get that isocyanate in CO. So polyurethane basically uh, they are not made upon heating and can then be useful as a thermosetting polymer. You can have this kind of isocyanate and then treat with hydroxyl group, so you can get the NaCO4. And then we are talking about the rubbers. So rubbers basically elastic materials. You can stretch it for your natural rubber or polyisoprene, right? That can be stretch it. But if you want synthetic rubber, so you can because the natural rubbers it will be vulnerable to acid or base condition. Okay, whereas synthetic rubbers they are flexible, stretchable at the same time. They don't need much time. So, for example, Buna A, so it is the 1,3-butadiene and A is your styrene. So, they will become forming just one by one sequentially. So, that's called that uh, synthetic rubber or Buna S. So, what is the uses? Manufacture of tires, cables, wires, all this. And Buna N is basically acrylonitrile, CH2 CHCN and 1,3-butadiene. So if you just go for copolymerization, you can have 1,3-butadiene and followed by styrene, and especially the double bond. Double bond is very much important. Okay, so what is the use? It is used versatile. It is used to manufacture parts for automobiles, aircraft. It also used for making conveyor belts, adhesives, and oil resistant. So another one is that bakelite. Bakelite basically phenol formaldehyde regions. Basically phenol and formaldehyde when it reacts, it will get that benzyl alcohol, hydroxybenzyl alcohol, and then it has to form that 3 hydroxymethyl alcohol. And once you go for this cationic polymerization, you can get the kind of OH-CH2, OH CH4, OH methyl aldose. Okay, so basically that formaldehyde and hydroxyl phenolic hydroxy group, they used to form the very link structure, bakelite. And bakelite is highly useful to make the rubber ball. Okay, so I'll stop here. Portland or butyl rubber. So all these things are there. So I'll stop here.